So in our last video we learned about an instantaneous rate of change, which is called the derivative. Here we're going to apply that to some projectile problems. I can't remember what else is in here. That's basically the idea. So we're going to try to find this in an application. I would want to know how a velocity is changing. So when you function here, this is a little physics stuff here, but S is displacement, so this is going to be the distance formula. So the instantaneous, so the derivative is velocity. So if you have a function that's about the distance, the derivative, the instantaneous rate of change of a distance is a velocity. How fast are you changing per some speed? So what we want to know here is they want to know the velocity at these two different times, at 1 and 3. So what we need is the instantaneous rate of change. What we need is the derivative, and if we have that general derivative equation, we can then put in 1 and 3 to find the specific rates of change at that point. Now here's the definition again. We did this in our last video. We're doing t plus h this time, but it's the same idea. Here's the definition of a derivative. Okay, crunched it all down, they took the limit and they got this. Now I didn't know if I should do this. I'm going to give you a shortcut here. This is what you learn. So if you were on a test and it says, hey, you've got to do this by the definition of a derivative, you have to do that. But if you have a polynomial like this, here's what winds up happening. The derivative is just going to be, this exponent is going to drop down and multiply by the front. So 2 times negative 16 is going to get me negative 32t. Like the exponent decreased by 1. So 2 times negative 16 is negative 32t, just to the first power now. Now there's a 1 on this t, so it's going to go and multiply, and it's going to get me 64. And then it's going to drop down to be t to the 0th. Well, that's anything to the 0th power is just 1. This doesn't have any t's at all, so it's just going to drop off. And so look, here is my derivative without having done everything. Look, they match. Without having done all that craziness of the definition. So that's the shortcut. It works on just a simple polynomial. And again, you'll get the full story in calculus. So if it asks for the definition, you would have to do this. We did this in the last video, but here's the derivative, a much easier way. Now we want to find what's happening to the velocity when time is 1. We'll just put in 1 for t, and you get 32. Put in 3 for t, you get negative 32. So that's telling us that the velocity here, we're going 32 feet per second going up. It's telling us the direction, and negative 32 coming down. So the negative's telling me that we went up, we went down. Okay, now if you want to practice your definition of derivative, you're welcome to do that. But do you see, I don't even know if this is the same equation. I think it is. If we were trying to find the derivative with my little shortcut here that I was saying, it'd be negative 32t plus 64. And that's it. So I think this is exactly the same one as before. What is the velocity 2 seconds into flight? We're just going to find the derivative when you've got a 2 in there. Okay, and so now this is going to be the top of the parabola. So this is going to be 64 plus 64. It's going to be 0. So at the very top, you started changing directions. You're not going up, you're not going down. Okay, so we're going to do this now from a graph, and I can't remember what else is coming. So first of all, they're just saying, hey, what's happening here? Evaluate this function when x is 0. Well, when x is 0, y is 1. Remember, this just means y. When that's 0, you get 1. Now, well, let's put 2 in there. Put 2 into the equation, and we get a value for the function of 1. Now, how about the derivative, though? They want us to say what's happening at the derivative when x is 0. Well, what we learned that is, another way of thinking this, it's the tangent line. It's a line tangent to the point at that spot. So a tangent line here would be a horizontal line. And horizontal lines have the change in y over the change in x. So the y is not changing. So it would be 0. The y's are always staying the same, something over x. So it has a 0 slope, and so the derivative here is 0. Just by drawing a graph, drawing that horizontal line there. Now, let's draw one. When x is 2, we want to find the derivative. And so we're going to draw a tangent line there, and we're going to do our best to estimate it. They actually did this for us here. So they drew a tangent line at that point, and we're going to do our best to estimate it. Well, we go up 1, 2, 3, 4 over 1 appears to be the slope of this line. So the derivative appears to be 4. Okay, so we're going to do the same thing again here. If I'm just evaluate these first. At 1, we get the function as 0. Just reading an old graph like the beginning of college algebra. So, oh, I'm sorry, that was this one. When x is 0, y is 0. When x is 1, y is -2. So this one would be -2. This would be 0. Now, how about the slopes? So how about the derivatives, the instantaneous rate of change? All those are synonyms. So when x is 1, we're here. So we'll draw a tangent line. That's a horizontal line again. So this derivative is 0. This instantaneous rate of change is 0. Because we're not going up or down, we're changing direction. And then how about when we're right here? Well, we would draw a tangent line. It's supposed to be something like this. So that's my best shot at it here. We'd be going 1, 2, 3 down over 1, I think is where it's supposed to hit. So it's supposed to be down 3 over 1 and a slope of -3. Okay, now this is a really confusing problem. They're being real technical about what's happening here, but basically they're saying, hey, find the derivative and tell me what's happening when you make 200 computers. So we're going to do this a polynomial, so we're just going to find our derivative the fast way. It's going to be 2x minus 100. And we want to know what happens if you put in the 200th computer. Well, it costs 400 minus 100. It's going to be 300. All right, now they're going to talk about interpreting these derivatives in context, and I think there's one more slide after this, but I don't like that one. I think it's a little too much for right now, so I think I'm going to skip it. So, but let's just talk about what these means. This is a story about distances in miles. So we're talking about the time. So x is going to represent time, and y is going to be miles. So if you have 0 going into the function, that's time. So when you've traveled 0 time, you've traveled 0 miles, right? Makes sense? Now let's jump to these before we go back to a derivative. Now, when f is 1, or when we put 1 into the machine, that means when we've gone 1 hour, we've gone 70 miles. And then lastly here for d, when we've gone 2.5 hours, we've gone 150 miles. So what does this one mean? Well, this one is an instantaneous rate of change. So the 60 is a slope. So when we put in time of 1, we're not getting out miles, we're getting out a slope. We're getting out a change of y over a change in x, which means we're getting a slope of 60 over 1, and y is 60 miles, and 1 represents hours. So when we have traveled 1 hour, what we're getting out is a slope. What we're getting out is a velocity, 60 miles per hour. It's a slope, 60 miles per 1 hour. That's the same thing as 60 miles per hour. When you put in this into the derivative formula, you're getting out velocities. You're getting out instantaneous rates of change. Now again, I'm skipping this last slide here. It's true, but I don't like what they're doing with eastward and westward. So I think that's, if you want to look at it in the back of the book, you can. I think that's too much. I think that's a little confusing. So we're going to leave it right there.